Howdy. We're ready for Fun Chem 1, the lab sections. We're going to knock out a series of the last few labs, kind of take care of them. So I'll be referring a lot to the lab book. And the first lab up is the molar relationships in a chemical reaction. All right. So this is a neat little reaction. The idea behind this is we're going to take some copper sulfate, which is this beautiful blue solution in water. This is our first case where we're going to use a reagent that is different than the reactant. The reactant, copper sulfate, anhydrous without any water, is actually quite dangerous. It's expensive. It's difficult to keep. But we can use copper sulfate pentahydrate, which already has 5 waters trapped in the crystal lattice for each copper, and so it gives it this blue color, having that water trapped, chelated around the copper. All right, and so when we mix this in water, we'll get the same product as we would, the same reactant as we would with the copper sulfate. And since that's the first step, mixing in water, we'll use the much cheaper, much safer copper sulfate pentahydrate. So when you see in the lab CuSO4.5H2O, you're not adding more water. That water is already trapped in the solid. It's trapped in the crystal lattice. Now, this is historically a great lab. This is a lab that you could, if you were a little bit shady, you could, in the past, claim to be an alchemist and try and make some money off of the rich patron or the king. And so we said alchemists wanted to turn lead into gold. So one of the classics on this is a bunch of sleight of hand. You can take a crucible and put a fake bottom in it with a little speck of gold, have the blacksmith pour in some molten lead, say some magic words, and it melts out the fake bottom, which maybe you made with sugar or salt or any kind of white looking compound that was down there and would melt easily. All right, they didn't really use sugar. They didn't have it readily available, but they had a lot of other compounds. And so you can do all kinds of sleight of hand, but this reaction is what really made a lot of people rich. All right, and so the key to it was you had to dig up this blue powder. It's easily available if you know where to look, and so you find some copper sulfate, and so you get a big quantity of it, and you pour a little bit into a vial, and you mix it with some water, and you get this beautiful blue magic looking potion. And we're going to take it to the king and tell him that we can turn iron, and he doesn't have to dig up lead. He can use iron from the blacksmith, and we're going to turn that into gold. And so you're going to provide the magic vial, and you let the king call in his blacksmith, his trusted advisors, everybody to make sure that you're on the up and up. And they come in, and you never touch the iron. You never touch the container. They put in a couple of shavings of iron, maybe pieces of an old nail or something, or just whatever iron they had laying around. And then you would add in a little bit of your magic solution. Make sure you pour it all in, maybe just a little small bottle, and you pour it in, and you would say some magic words and do some stuff, but you never touched the container. All you did, you could even let the king add the magic potion. That's fine, but you've got to have some real um, authentic sounding magic words. So when I ask students to do this, they always say abracadabra and hocus pocus, and it's always the same, and so their reaction doesn't work very good, right? But instead, you will come up with your magic words, and the reaction takes place. So we'll be using iron powder, and so we're just going to use the powdered form because more surface area makes this reaction go faster. But this will work on on even a nail. It'll just react with the outside surface. And when we're done, we're going to get this copper solution. Now you may say, hey, that looks like gold, but the money is not in saying, trying to convince somebody that's gold. The money is in convincing somebody, hey, we almost made gold. We stopped at copper. If we'd had more magic solution, we could have made gold. And so then you would tell the king, you need a lab, you need a setup, and so the king would get you uh, some money and some lab work, and every time he'd come in, you'd have a little bit more blue solution dripping, and then it was just a matter of how many times can you get more and more money uh, before he realizes that no matter how many times he tests this, he's always going to get copper. Now, where was the copper coming from? It was coming from our blue magic solution. It was in solution already. Where does the iron go? It'll go into solution. All right, and so this reaction is pretty straightforward. Yeah, there we go. So, but it's our first example. So we're going to take our iron plus CuSO4, and it'll go to FeSO4 plus Cu. And I'm going to write that down here, plus Cu. All right, and so this is our first good example of this, where we have a single displacement, but it's also an oxidation reduction. All right, and so this is our intro to an oxidation reduction. So our formula for single displacement then, remember, was A plus BC, and it went to AC plus B. All right, and we noticed that the charge on the iron, when it started off, it had no charge. There's no charge here, all right, and the charge on the copper, we have to figure out its charge. Well, it's 1 copper. We don't know its charge. And sulfate, we only have one of those. Remember, there's parentheses 1. And it has a -2 charge because we memorized it. And the total charge for this compound is 0. So X would be 2. So this is a copper that's a +2. Now on the other side, this copper is a free element. It's by itself with nothing indicated, so it has a 0 charge. And the iron, we can do the same math, and we also come out with it is a +2 as well. All right, and so the copper and the iron swapped places, but they did more than that. They transferred some electrons, and so the iron Fe lost 2 electrons. Remember, it went from a 0 to a +2. It gained a charge, a positive charge, but it did that by losing negative charged electrons. All right, so copper gained 2 electrons. Now, where did it get the 2 electrons? Well, it got them from the iron. Where did these go? They went to the copper. All right, and so this transfer of electrons, it's the basis behind our chemistry and our electricity, the chemistry behind electricity. But for us, this is actually just a nice simple example of a redox reaction, an oxidation reduction. And so we've got lots of terms that they throw around in this chapter, and so we'll get a basic idea here. So 3 definitions: oxidation and reduction. We want 3 definitions for each of those. So I've got some previous videos on how to tell those apart. This is chapter 8. So oxidation is gaining oxygen. Reduction then would be losing oxygen. Oxidation is also then going to be losing hydrogen, and then it'll also lose electrons. And so reductions will be gaining. Notice it's the opposite of the oxygen. So it's going to gain hydrogen or gain electrons. All right. Now we can go through a lot of different ways of memorizing this and keeping up with it. I like to look at the charge, um, and so I think of this as an elevator. So my ground floor is at 0, first floor of the basement, second floor of the basement. Notice they get bigger as you go negative. And so reduction in height is this way, and oxidation would be going up. All right. And so the iron went from a 0 up to a +2, so it was oxidized. We can also get that by the fact that the iron lost 2 electrons. All right. The copper went from a +2 down to a 0. It was reduced in height, and so it gained electrons, so it was reduced. Okay. Now, lots of ways of keeping up with that, but what we also then have to worry about is this other set of terms, and that is oxidizing agent and reducing agent. Now, in the back of your lab book, there's a handout that I used to give out. It has all of these kind of notes, and so it's a nice handy thing there. It's backed by your color periodic table in the back, the white pages in the very back of um, your notebook. I don't have that handy with me. Mine, of course, predates that copy. Um, and so we need to worry about oxidizing agent and reducing agent. Now, an oxidizing agent causes something else to be oxidized, and a reducing agent causes something else to be reduced. The easiest way to do this is treat the word agent as if it flips the meaning. So to find the oxidizing agent, it's what was reduced. Well, the copper gained 2 electrons, and in doing that, it allowed the iron to lose electrons, thus allowing the iron to be oxidized. So the fact that copper was reduced makes it the oxidizing agent. And the fact that iron was oxidized makes it the reducing agent. And we can just label those like that. Now, we transferred how many electrons? 2. Don't add them up. It's one lost 2 electrons and one gained 2 electrons. So if I transfer money to the bank, I lose the money, they gain the money. That's the easiest way of thinking about that. All right. Now, all that's going on in this reaction, I'll link a video on Blackboard, and we'll watch this reaction actually take place. But the problem becomes the calculations. They can be a little overwhelming at first. So the reaction itself is nice and easy. You mix them together. You get everything. You do everything in water. We could mix the solids, the iron powder. We can mix this iron powder with the copper sulfate powder. It'll eventually react. A couple hundred years, it'll all be done. But if we dissolve one of these in water, then it works out really well. It goes within 20 minutes or so of stirring it. And we also see a nice thing is if we use the iron as the limiting reagent, so the extra copper sulfate dissolves and the iron sulfate that forms is also soluble in water, then that gets washed away. And so what we do with this when we're done is we wash it a bunch of times with water, and the copper that's formed will be left behind as a solid. And we don't want to have any iron left behind. We want to use it all up. All right. And then, so after washing it a bunch of times, then we rinse it a couple of times with acetone. And the whole idea of the acetone is it displaces the water. It gets the water, kicks it out of the way so that there's now acetone coating all our copper. And acetone has a much lower boiling point. And so we can evaporate it off really fast by putting it on a hot plate and drying it out really fast. All right, so we'll just heat the copper up and in an evaporating dish, and it dries out super fast, nice and easy. And so at the end, we'll be able to measure how much copper we formed. Now, the idea here was to decide on the molar relationship All right, and that is given by the balanced chemical equation. But this one is already balanced at 1 to 1. And so for each 1 mole of iron I put in, I should get 1 mole of copper out. And so what we'll do is we'll figure out how many moles we started with of iron and how many moles we started with copper, and to get that ratio. All right, and the way that you get a ratio, let's say I have 4.2 and 2.1, and I want to get the ratio between these two. The easiest way to do this is take however many numbers you have and divide them all by whichever one is the smallest. So here I'm going to divide them both by 2.1, and this one divided by 2.1. And so this one is 2, and this 2.1 that becomes 1. So it's something to 1. It's something bigger than 1 to 1. And that's the easiest way to get a ratio. Nice and easy. All right. So let's knock out this pre-lab and get a feel for what's going on. So the first thing it did was ask for a balanced chemical equation. We did that. It then asked for the molar mass of CuSO4. So let's review how to do this. I'm going to, when it says molar mass, I'm going to go to my periodic table, and so when I'm over here, I'm going to find the copper, and I'm going to get the number underneath it. Now this one's a little bit tough to read, and then I'm going to find the S, and then I'll find the oxygens. Remember, there's 4 oxygens here. All right, so I'm going to whip out the periodic table we use in our book. All right, so it's just a little bit easier for me to read. I've got 63.55 plus 32.07 plus 4 times 16.00. And I do all that math, and I'll get some number, 159.62. Now I should have 4 sig figs, but I'm not going to worry about it right now. Grams per mole. And that's how you find the molar mass. So when it asked me to do FeSO4, which I don't know why they decided to do that, just for practice, I guess, then it's the same kind of idea. Fe would be 55.85 plus 32.07 plus 4 times 16. And type all that in, I'll get an answer in grams per mole. That's right out of chapter 4. Good practice, good review. So this is a lab that kind of links chapter 4 with chapter 8. So it's got a little bit of both in there. And we see that trend for the next few labs that they cover more than one chapter. All right, so the next one I'm looking at over here, it says, what is the purpose of acetone? We already talked about what that was. And it says, what should you do with the waste rinse acetone? Well, anytime you use acetone, it should not go down the drain, and so it needs to be put in the waste container. All right, and so that's easy enough. And then it says we're going to start with so much iron, and it wants to know how many grams of copper. So it started with 1.753 grams of iron, and it wants us to go to grams of copper. Oh, this is right out of chapter 4. All right, so we're going to be using our roadmap. So let's get a quick drawing of this. We'll go from grams of Fe to moles of Fe. We'll cross our Scurry River to go to moles of copper, and then we can go up to grams of copper. Now, going grams to moles is molar mass. We get that off the periodic table. Over here, we'll be using the molar mass. Now, how do you go from moles to moles? Well, if it's two things, if they were part of a whole, we would use the chemical formula. But here we're going to use our balanced chemical equation. And so here we know it was 1 to 1 because of our coefficients for our equation. So let's go ahead and just 1.753 grams of Fe. I need grams of Fe on the bottom and 1 mole of Fe on the top. 1 mole of Fe will go to 1 mole of copper. Make sure I have room. All right. 1 mole of copper goes to so many grams of copper. So now I'm going to look these numbers up. So I look up Fe, and it was 55.85. So that would go here. 5.85. And then over here, I'd have my copper in 63.55. 63.55. All right. And then I'll let you type that in. 1.753 times 63.55 divided by 55.85. And I ignored all the other ones. Not too big a deal. We'll get our grams out at the end. All right. That would be our, remember, that is our theoretical yield. So how much we could have made. And then at the end we would find out how much we actually made. And so if it asks us to get the percent yield, it'll be actual divided by theoretical times 100. But they also like to ask us about the error. So percent error. All right. And that's going to be the absolute value of the actual minus the theoretical. I'll abbreviate here. Over the theoretical times 100. All right. So they may ask us to do that and in the lab. So those are those calculations just in case we need them. So I'm going to go ahead and read on the next part of the lab. It says they look dry. How is this going to affect the mass of copper? All right, so they look dry. That means that there's still probably some acetone. They skipped that last step. They didn't cook off the acetone properly, and that's what they're saying. So what's that gonna do? It's gonna leave some acetone behind. All right, so yeah, that's gonna cause their mass of copper to be higher. Well, if the mass of copper, what's that do to the moles of copper? Well, remember, you're going to take your grams of Cu, and 1 mole of Cu is 63.55. So we divide it. So if this number goes up, then my answer here will also go up. So that's simple. All right. So that's easy enough. Now what I would do is, like I said, I'm going to link a video. You'll watch the video of somebody doing a very similar experiment, okay? But instead what I'm going to do is I'm going to go through and do some of these some of the numbers and calculations with some example numbers. Now, I'll give you some different numbers when we're ready to do the actual lab. So these are the numbers I'll be working with. So I'm going to be starting off with 1.346 grams of copper sulfate pentahydrate, and we'll have 1.030 grams of iron. Then, so that's my gray powder, right? And then at the end, then I'll do the reaction. Basically, I'll dissolve the copper sulfate, then I'll dump in the iron, stir it up, say my magic words, that's the key, and then I'm going to let that sit and react for around 15-20 minutes, and then I'm going to pour the liquid off and leave the solid behind. That fancy word, that's decant. And then I'll wash it a whole bunch of times with water, and then I'll wash it with acetone. And so I'll measure out an empty evaporating dish, measure out this empty evaporating dish, and then I'll add transfer my solid over there, my copper, and I'll mix in some acetone, wash it a couple times in the evaporating dish, and then I'll heat that evaporating dish and cook off all the acetone so that I'll get a powdered copper, and it should look like this powder here. It should be nice and dry and work great. All right, and so let's get a look at these calculations. So I'm going to use those numbers and do some of this calculation. So it says first find the moles of Fe. People love to leave that one off. So I had 1.030 grams of Fe, and I'm going to take that to moles. All right, so I'm going to take that number and I'm going to divide it by 55.85 grams of Fe is 1 mole of Fe. All right, and just getting that off my periodic table, 55.85. All right, so all right, pull up my calculator and I do that number real quick. All right, and I got 0.018. Now I had 4 sig figs when I started, 4 sig figs here, and so remember that 0 doesn't count. So 44226, and then I'm going to say equals 0.01844 moles of Fe. Now it asked me to show all that work, so no problem. Then it says you do the evaporating dish, you do the mash of the evaporating dish in the copper, and it wants to know how many grams of copper. All right, so I'm just going to subtract those out. So I'll take my 68.44 minus 67.421, and that'll get me my grams of copper, 1.019 grams of Cu. Now keep in mind, it's 1-to-1 in the equation. That doesn't mean grams to grams. It needs to be 1-to-1 in moles. So I'm going to go ahead and take this over to moles. It also asks me that. All right, and the molar mass of copper is 63.55 grams of copper for 1 mole of copper. So I'll take my 1.019 divided by 63.55, and I get, let's see if I can remove here, 0.0160346. All right, now 4 sig figs, 0.01603 moles of Cu. Okay, not a problem. All right, and so then it asked me write the balanced equation. Hey, that's right off the pre-lab. We did that earlier. Then it says what's being oxidized, what's being reduced. Remember, what's being oxidized is what loses the electrons. Now, I'm going to use, I remember I said there were 3 definitions. I'm going to look at this again. Fe plus CuSO4 goes to FeSO4 plus Cu. I said there were 3 definitions. One of those definitions talked about the oxygen. How much oxygen is with the iron? None. How much is with it in the product side? More than none. It's got some. It gained oxygen. So the oxygen was oxidized. The copper was with oxygen. Now it's not. It was reduced. Now the SuL4 is just along for the ride. The copper is what was reduced. All right. If it's oxidized, that makes it the reducing agent. If it's reduced, it's the oxidizing agent. How many electrons were transferred? Remember, this went from a 0 to a +2, and you have to do your math to figure that out. All right, and then it says, what is the ratio? Well, this is 1 to 1, so 1 to 1. And then it says, what is my ratio? Now, my ratio, and it asks me, it says Cu to Fe. So I'm going to do it this way. And so I'm going to put 0.01603 moles of Cu to 0.01844 moles of Fe. But this is terrible. Nobody likes this. All right. So what I'm going to do is divide them both by the smallest. This one is my smallest. It'll be 1. So I don't really have to type anything for that. 0.01844 divided by 0.01603. And this is 1.15. So my ratio would be, in this one, 1.15. Keep in mind, these are not the numbers that you'll use in the lab. I'll give you different numbers. You're going to do these same kind of calculations. It's going to ask sources of error. Okay, I probably won't ask that. Describe the iron before the reaction. Describe the solution before the reaction. Describe it after. That one, it's a little tougher. It depends on how much extra copper sulfate we use. It's a little bluish, but if we did this where there's almost no extra copper sulfate, it actually turns from blue to green. It's kind of pretty. Um, and then this is done aqueous, not, we talked about why it was done aqueous and not in solid form. All right, so this reaction, I'll give you some different numbers. You're going to run through, you're going to watch whatever video I happen to search up on somebody doing this reaction. It's, like I say, a classic reaction. And so the calculations can be a little interesting and overwhelming at first, but they're not so bad. All right, so we'll catch you on the next one.